Quick recap from lecture last time. We had the standard two numbers. We have our two generator numbers, 0 and 1. And then we define the operation of addition. As soon as we add 1, then we generated the natural numbers. As soon as we wanted to undo addition, we generated the integers. And then we added in multiplication. As soon as we wanted to undo multiplication, then we generated the rationals. So these are the algebraic numbers, as opposed to the real numbers that we'll do in this class. So the algebraic numbers are defined with these algebraic identities. And instead of thinking of algebra, I'm going to think about them in terms of mappings, because that's the more modern way of thinking about it, and you get you a lot more traction. So addition, an ordered pair goes in, one ordered pair goes in, one number comes out. So that's a function. Going backwards, it is not a function. Do a quick sanity check to see why not. X plus y, feed it through the addition function and get 7. I graph that set and I get all the numbers on this line. So when I undo, it's not a function. So we don't even give it a name, because one number 7 goes in, an uncountable number of ordered pairs comes out, not a function. It's a set valued object, which is fine, but that's for a different class and different scenarios. Instead, we want to think about if I restrict one of the inputs to make it a one-dimensional function, dimensions match, and now suddenly it's invertible. So I undo this thing and I get out 4. Normally the way we do this then, instead of just giving this the undo name, is I'm not even giving a name because we're not going to use it this way. When I fix one of the inputs, I'll instead write it like this. And so the X goes into the blank space in front of the plus sign. So then the undoer is subtracting 3. But instead of course, there is no subtraction. There's only the addition of negative numbers. And so we agree that that notation, -3, means add a negative number. Now it's a function, and it's a function in both ways, and everything's cool. In exactly the same way, multiplication works, where if I have x and y, and I feed it through the multiplication operator, and I get 7, then I'm saying this whole product is 7, which gives me a uncountable number of ordered pairs. So the inverse is not a function. But if I restrict one of my inputs, now it's a one-dimensional function, and then when I go backwards, I get one answer, 7/3. And similarly, we'll redefine this operation this way. Multiply by 3, and you get 7. So divide by 3, and you go backwards. Of course, there is no division. There's only multiplication by reciprocals. So whenever we see the division sign, we'll agree that that means multiply by the reciprocal. So now we have 4 operations. We have adding, we have multiplying, we have take the negative from the additive identity, and we have take the reciprocal from the multiplicative identity. So we have these 2 new operations, take the negative of something, so 3 goes in, -3 comes out, and take the reciprocal of something. 3 goes in, 1/3 comes out. They're, of course, undone by themselves, so that makes them nice operators. Why do they get undone by themselves? You have to prove it. And I'll leave that as an exercise for you to do, because it's easy. Well, it's easy once you see it. I should always say, not easy, but straightforward, meaning It's just from the definitions. It's from the definitions. In particular, we're leveraging uniqueness. That's always the key. We're leveraging the uniqueness. Okay. Now we want to transition from the rationals to the reals. This transition, we have to do limits. That's the function that gives me the extension. When I take the limit of a rational number, I get a real number. What's a limit mean? What do we mean exactly by this? Right? It turns out it's complicated. So instead of doing that route, we're going to do the easier route with something called the supremum property, which is exactly equivalent to the limit property. It's just easier to get a hold of. You can prove one implies the other, so they're equivalent definitions. So we're going to do supremums. There's the transition. Okay, what is a supremum? A supremum is a least upper bound. All right, now we're getting somewhere. Upper bound. Well, let's do an example. So I've got a line of numbers. So I've got my number line, and I'm only in the rational space. It's solid because the rationals are infinitely dense. Between any two rational pixels, there's a pixel in between that's rational. And you can do this as much as you want, so it's always going to be a solid line. But of course it's not solid because there's numbers that aren't in there, like pi, or square root 2, or square root 3, or e, or, right? All sorts of numbers that are not there. So that's a hole in the line. Another way of saying the transition from rationals to reals is that you take the completion of the rationals. And we'll see what that is later, but that'll be near the end of the course where we finally get that defined. This will be basically the end of the course is we'll say, oh, it's just the completion. And these are all the same thing. It's just a matter of building up the definitions and building up the machinery. Completion is kind of what you'd think. You just fill in all the holes. No matter if it's infinitely dense, there's still holes in it. Fill in all the holes. Now it's completed. And you make a new set. You've added in new points. You've made a new set. Okay. So let me grab a bunch of points here. I'm going to call this the set S. So S is the set of rational numbers such that they're all less than or equal to 3. Sweet. So 3 is an upper bound. For S. So is pi. So is 5. But 3 is the least of the upper bounds. Meaning anything less than 3 is not an upper bound. There we go. Well, that's it. So, the real numbers. So the real numbers are all the rational numbers union all the supremums of sets of rational numbers. That's one way to think about it. So a supremum is just a marker. If that marker doesn't exist, you have to make it a new number and add it into the set. Now you've made more numbers, and now it's the reals. So let's do some definitions here. All this is true, but now let's just be more precise about what all this means exactly. So upper bound means this definition. So when you say these words, there's always a logic statement behind it, because the logic statement is precise, words are not precise. 3 is an upper bound of S means for all elements of S, for any element you pick, for an arbitrary element of S, R is less than or equal to 3. Done. That's it. That's an easy definition. And it fits with exactly with where you'd draw things on the number line. So pi is an upper bound because everything in S is less than or equal to pi. It never is equal, but it doesn't have to be because it's or, less than or equal. One of them's true, it's true. So 3 is an upper bound of S. 3 is a supremum. So let me be more precise there. Let's just write it down how we're going to write it. 3 equals the supremum of S means two things. One, 3 is an upper bound, which we already have the definition of. Two, anything less than 3 is not. Is not an upper bound of S. Okay. The 3 is an upper bound of S we already have. Instead of saying 1 and 2, let's be a little more mathy with all this, because it's easy to get the numbers that are all confused off, and so we'll use the fancy math 1 and 2. So 2 conditions. It's an upper bound. Anything less is not. We already have the definition upper bound, so we can negate it. Flip the quantifiers, negate the statement. So there's the definition of 3 is not an upper bound. Of course, we're not looking at 3. We're looking at something, anything less than 3. Okay, so let's make this into a more precise thing. So instead of saying 3 in this, this is saying 3 is not an upper bound. Instead of saying 3, we want something less than 3. So we want 3 minus a little bit, minus a little delta. Well, how many little deltas? Any. I take any positive decrement. Now that is anything less than 3. Can be written like that. I'm on the number line. There's 3. There's a number less than 3. How do I want to describe it? I can take a distance backwards. What's the definition of delta? Head minus tail. So 3 minus the mystery number is delta. Right? So easy. That is not an upper bound, so that is below some element. That is below some element. Quantifiers matter, so that happens after the choosing. So the quantifiers matter, so I first have to pick a number less than 3. Then that thing is not an upper bound, so then I insert the definition from above. So now there exists some element of S that's bigger. Let's put that on the number line, just see what we're looking at here. So here we got our number line. Here's our number 3. Here's our number 3 minus delta, something less. And now I have to pick an R that's bigger. Well, that's easily done. We just put it right there. Midpoint, for instance. Which you can always do, because that's a rational thing. Take 2 rational numbers, divide by 2, rational number. Add to a rational number, rational number. So everything's rational. What I'm kind of futzing here is I'm saying, oh, then you're saying delta's rational? No, because it's anything. And now we're in the reals, and so this can be a real. All right, so that means if I just take midpoint, it might not be rational. Fine. Well, now just pick a rational number arbitrarily close to this delta. Right? You can see that you can jigger it. It is jiggerable. So there's our definition of supremum. Two definitions. So it's a two-parter. This is what, somehow this makes people's brains explode, and I don't know why. But here it is. First part, 3 is a supremum means this statement. It means, first of all, every element of S is less than or equal to 3. Second of all, it means this mouthful. That anything less than 3 is not an upper bound. So I just take the not an upper bound and rewrite it. Notice I flipped this. That's just me because I always had trouble in grade school figuring out where the things go. And so I always put the smaller one on the left, and then it's the alligator who wants the bigger meal. And I'm right-handed, so my left hand makes the less than or equal sign. So it's just habit. I'm just going to do it because then it's easy for me to plot it. 3 goes here, and then I go over a little bit, and then R goes there. Right? It's that kind of thing. So this is saying 3 minus delta is not an upper bound. And here I'm saying any delta. For any delta, positive. 3 minus delta is not an upper bound. So anything less than 3 is not an upper bound. There's a corresponding inverse property called infimum. Which is exactly the same as supremum, except other way around. It's the greatest lower bound. And the definitions are all the same. So you can say that 3 is the infimum of a set S means two things. First of all, for any element in this set S, 3 is a lower bound. So everything is bigger than or equal to 3. It's the greatest lower bound, means if I pick anything bigger than 3 is not a lower bound. So flip the quantifier for not, and there's our definition. Same thing. Three plus delta is not a lower bound. Finally, we can get to limits. Well, before we do limits, we need to define sequences. Before we can do sequences, we need limit infimum and limit supremum. So let me just start with sequences. A sequence is a mapping from the natural numbers to some field. That's a sequence. It's a mapping from the naturals to the reals. So if some natural number goes in, some real number comes out. And we do subscripts instead of parentheses. So this really should be the sequence generator giving me some real number. Okay, that's a sequence. So I have x0, x1, x2, dot, 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 dot. That is the image of the sequence, the result of the sequence, which will confusingly just say sequence. The sequence is really a function, and we'll call it also the output of that function, just to make our life simple. And so the set of these things we'll denote this way. We'll just say it's all the sequence elements where n goes from 0 to infinity. We'll use that notation. So there's my sequence. And often we won't even say, we'll just say x sub n, and then we're like, oh, everybody knows. Right? It's that kind of thing. Okay. The limit supremum of xn as n goes to infinity. This has a specific definition, and here it is. It is the infimum of the set such that capital N is a natural number. S sub n is the supremum of the set, all sequence elements where the element is bigger than or equal to capital N. That's the lim sup. So it's only defined in terms of infs and sups of sets of numbers, which we've already done. So it's a two-stage pass. This is kind of an awkward thing to write down, and so instead we write it in terms of subscripts. Same thing. And this one we can write even more compactly like this. So just like when we write trig functions, we say, oh, we just say sine theta. We know there's parentheses there, but it's such a pain to put them in, and it confuses things. So we just leave them off. This is exactly the same thing as we're doing right here. Is we know that inf and sup are set-based functions, and so there's set notation brackets everywhere. We're just leaving them off because we know they're there. Just like when we say y equals x squared, we leave off set bracket, all ordered pairs xy, such that y equals x squared, close set bracket. We know it's there, and it just makes everything longer, and so we just drop it. Same thing here. This means this. So it's nested. It's a nested thing. So you start here. This is the set of your sequence, which gets fed into here, which extracts the tail of the sequence. And anything up to capital N is the head. Everything past is the tail. So I just look at the tail of the sequence and take the biggest thing I see. And then I take the infimum over all those. That's my lim sup. Lim inf is going to be exactly analogous, except the other direction. It's going to be the supremums of the infimums. So I start again. I start in here, take the sequence. I look at the tail of the sequence and take the smallest thing I see. And then I take the supremum of all of those. With these definitions, now I can say what the limit is. The limit of a sequence. It's some number where the lim sup and the lim inf agree. There's our definition. There's the limit of a sequence. The lim sup equals the lim inf. So it's all just in terms of supremums and infimums. So we're going to use this as our major tool. This is going to be the major tool we'll use in this class. Let's do an example just to finish things off. Let's look at this sequence. Nice and easy, right? Always want to start easy. Let's look at the lim sup. Here I'm leaving off the n goes to infinity on the bottom because there's only one index n, and so it's unambiguous what I'm talking about. And this is pretty standard. Because, of course, we're lazy. So this is the infimum over all n, the supremum, indices bigger than n of 1 over n. So we go inside out. I look at the supremum first. That's the first element. Because n is less than n plus 1. So 1 over n is greater than 1 over n plus 1. So as I increase my index, I decrease my function values. So remember that the index is what you call the input, and then the value is the output. And then the mapping is your sequence. So as my index increases, my value decreases, so the supremum is the first element. You have to prove this. Easy to prove. Now we take the smallest of this collection of capital N's. So now I have a new index. So now my index is capital N, and my value is a 1 over n. And I'm running through all of the natural numbers. This is a monotonically decreasing function, and so its infimum is 0. I look at the lim_inf. It's the supremum over capital N's, infimums over all the indices in the tail, these are zeros, the supremum of a set of zeros, 0. The lim_sup equals the lim_inf, and so we can say the limit of the xn is 0. Of course, these are all n goes to infinity, n goes to infinity. We're going to be doing so many limits that we'll end up dropping the n goes to infinity pretty quick until we get to multiple indices where it's confusing about what I'm talking about. But for now, that's where it is. Homework. Prove this. So you have to prove this. Prove this. In other words, use the definition of supremum to prove that's true. Prove this. Use the definition of infimum to show that's true. Prove this. The definition of infimum to show that's true. The supremum of 0 is 0. That's obvious. All right, now, just to be clear, this is not a number. This is a set. This is the set 0, 0, 0, 0, dot, 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 dot. It's the set of zeros where my index goes from n to infinity. So I'm at index n, I'm at index n plus 1, I'm at index x plus 2, da, 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 and they're all zeros. So the supremum of a set of zeros, obviously 0. Well, maybe not obviously. That's probably something to prove. Yeah. Prove that too. That'll be the one to start with because that'll be nice and easy. Prove this is also true. Prove these 4 equality signs. Prove that supremum is 1 over n. Prove that infimum is 0. Prove that supremum is 0. That'll do it. Monday is a holiday, so we'll see you all Wednesday.